Hello, and welcome to the Week 3 set of lectures of Digital Integrated Circuit Design with Dr. Mark Narden. In this week's set of lectures, we'll be going over two overarching topics. One is going into a little bit more detail on the actual voltage levels and transition times as we try to switch our digital circuits between 0 and 1. Second main section will deal with how do we actually send those signals through the circuit, capture the values, and the timing effects of basically trying to do logic and capture values and then do another set of logic, etc. And so how does the timing, kind of the basics of the timing in that type of arena. So here's a brief outline of what we'll be going through in the first section of lectures. First, we'll be talking in more detail about pass transistors, so using a transistor to just pass a value through. We've gone through basics of this in the past, but we'll go into a little bit more detail. Next, we'll be talking about the DC response of those circuits, and followed by that, talking about actual, again, we've talked about logic levels 0 and 1, but we'll be going into the details of noise margins, and I'll explain that when we get to it. Then transient response, so basically how does, when you change the input to a given logic function or a given circuit, how does the output change over time? It doesn't immediately go to the new value. And then finally, we'll be talking about more in RC delay models, so resistance and capacitance. There are parasitic resistance and capacitance in our circuits. So how do we model those and then estimate our overall delay? So we've talked about pass transistors in the past, but we haven't gone into great detail in exactly how they work. But in the past, I've mentioned that we always assume that for a NMOS transistor, so here I'm on the right, we're showing an NMOS transistor, and if you were passing a value through it, typically the input is the source, output is the drain. So if we have the source connected to VDD, we're trying to pass a 1 value through the NMOS transistor. And in the past, we've always said, well, the NMOS should always be connected to ground. But in this case, we're saying we don't have it connected to ground. We have it connected to something greater than ground. So we're trying to, for example, pass a 1 or VDD value through an NMOS transistor. Now, also keep in mind, I've said in the past that these transistors are created to be symmetric. So the drain usually is our output, the source is our input, but you could also think of it as, well, the drain could really be on either side, the source could really be on either side. So if we think about this transistor a little bit differently and we say, well, VDD is our input to this transistor, but we're going to connect that up to the drain of the NMOS, and we're going to use the NMOS to try and pull the source up to VDD. In this case, let's see what happens. So we have VG equal to VDD. Now, if our source is our output, if the V source is greater than VDD minus VT, then that means VGS is less than VT. So the transistor would turn itself off. So what I'm saying is, if the output of this transistor on the very right-hand side is pulling up in voltage, as soon as it gets to a threshold voltage less than VDD, we now have the gate to source, if the source is on the right-hand side, the gate to source voltage is equal to VDD minus VT, or VGS minus VT. Then as soon as it becomes equal to the threshold voltage below VT, the transistor turns itself off. So in effect, what I'm saying here, last bullet point, is the NMOS transistor as a pass transistor can't pull any higher than one threshold voltage below VDD. So VDD minus VT is the highest it pulls up to before it turns itself off. So this, while it's trying to pull all the way to VDD, it can't get there. It's still considered to be a quote-unquote high voltage value, so it's considered to be a logic value 1, but it's a degraded one. And the final point is, as we approach that VDD minus VT value, it starts approaching that value slower and slower, because as it gets closer and closer, the drain to source current slows down significantly according to the square law. So we wind up being a degraded one, and we also get there fairly slowly. So let's talk a little bit more on if we hook up some of these pass transistor circuits in slightly different ways. So let's start with the pass transistor in the upper left. This is what we went through in the previous slide. So what value can we get out of this pass transistor connected with the gate, and you can call it the drain or the source, connected to VDD. The output in this case, we said from the previous foil, is the output source is going to equal VDD minus VT is the highest voltage that we can get out of that. So now that we know that, if we hook it up instead like we have in the upper right, what if we put 3 of these types of pass gates in series with each other? What value would you expect to get out at the output of the right hand side after you go through 3 of them? Think about that for a second and pause. Okay, so now that you've thought about that, what actually happens is the output of the first one will go up to a threshold voltage below VTT or VDD. The second one, since its gate is connected to VDD and the transistor won't turn itself off until you get to within a threshold voltage of the gate, its output will also go up to VDD minus VT. And again, for the third one, it will also go up to VDD minus VT. So you will get VDD minus VT out of each of them because it's dependent on the gate to source threshold voltage. Since the gate is all the way at VDD, the output source can go to VDD minus VT. Now let's look at the PMOS transistor in the lower left. This is kind of flipped from the NMOS transistor, so you would think it should be similar in behavior. So think about it for a second and pause. So the output of the PMOS transistor with its gate connected to ground and its drain connected to ground would be 1 threshold voltage above ground, above the gate value, which is ground. So it would be able to pull down not quite to 0, but down to VT, which is the threshold voltage for your VTP, which is the threshold voltage for your PMOS transistor. Finally, let's look at the lower right corner. If we have the output of a pass gate, NMOS connected pass gate to VDD going to the gate of another pass gate, what output voltage do we get from the second one? Pause for a second. So in this case, the output of the first one is the same as we've been looking at, VDD minus VT. The output of the second one has to be 1 threshold voltage below the gate of its transistor. Since that gate transistor is at VDD minus VT, 1 threshold voltage below that is minus 2 VT from VDD. So you can see it gets really dangerous to have the output if you're using an NMOS only as a transmission gate, using the output of that to go to a gate of another device, especially another transmission gate, can get very dangerous. So it's not something we typically want to do, to cascade pass transistors with other pass transistors as a general rule. Next, let's talk about the DC response of our circuits to Vin, what Vout is versus Vin. We have been assuming that our Vin for our logic gates is always either a logical 0 or 1, which is either at 0 volts or at VDD. We've just seen in the previous discussion on pass transistors, there could be situations where you're not fully at 0 or VDD. But let's look at an example here. If we have an inverter, when Vin is 0, that means that the NMOS gate is fully turned off, PMOS gate is fully turned on. So we will pull the output value to VDD, and conversely, when Vin is VDD, the output value will be 0, as long as we give enough time to get all the way to VDD or 0. If, on the other hand, our input voltage Vin is somewhere between 0 and VDD, then Vout will now depend on how much either the NMOS or PMOS are turned on and the transistor size of the PMOS versus the NMOS. Thus, how much each one is turned on, the voltage level, and the transistor size will determine the current going through the PMOS and NMOS. And by Kirchhoff's current laws, that the current must eventually settle on the current through the drain of the NMOS and the current through the drain to source of the PMOS have to equal each other, and because our currents in our circuit have to equal, this is assuming that the current going to whatever load you have is 0, and so we need to solve for those equations. We could go through the equations for how to solve it, but in this particular case, looking at it graphically gives a little bit more insight. So I'll be going through some of the equations, but also the graphical insight over the next few foils to explain this. So our transistor operation, the current depends on what region we're in for the transistor behavior. And we've talked about transistor operating regions in previous discussions and in previous classes. So for what value of Vin and Vout are NMOS and PMOS in the 3 different regions that PMOS and NMOS can be in. So the cutoff region, the linear region, and the saturation region. So we'll be going through that again here to make sure that it's refreshed in your memory. So let's go through more detail of the 3 regions of operation for an NMOS transistor. You can see in the lower right-hand corner, if we have Vin, the NMOS transistor is the one highlighted in green. So we have the first region of operation is cutoff when the transistor isn't on. So the value of VGS for the NMOS has to be less than the threshold voltage for the NMOS. And if it is, then the NMOS does not conduct any current and the NMOS is off. For the linear region, we have requirements for both the VGS of the NMOS and the drain to source voltage through the NMOS. So the gate to source voltage has to be greater than the threshold voltage for the NMOS, VTN, and the drain to source voltage has to be less than VGS minus VT. So as long as the drain to source voltage is higher than the gate to source minus VT, we're not in the linear region. But if the drain to source voltage is less than the gate to source voltage minus VT, so it's a lot of times it's a fairly small voltage. If Vin is just barely over VT, then you have to go fairly far down before you're in the linear region. And then of course saturation region, your VGS again is greater than the threshold voltage, and your drain to source voltage is greater than VGS minus VT, and that's when you're in saturation region. So let's put this in terms of, we've been talking about VGS and VDS, let's put it in terms of Vin and Vout instead. So VGS is equal to Vin because the Vn is relative to ground, and so it's the same Vn as Vg. And VDS is equal to Vout because again source is connected to ground. So if we do all of these equations again, for cutoff, our Vn has to be less than the threshold voltage. If Vn is less than the threshold voltage for the NMOS, we're in cutoff. In linear region, as long as Vn is greater than our threshold voltage, and for Vout has to be less than Vin minus the threshold voltage. And then again in saturation region, if Vn is greater than our threshold voltage and Vout is greater than Vn minus the threshold voltage, then we're in saturation. So for PMOS operation, I'm not going to go through all of the equations in the chart that are in black, but I'll go through the ones that are in terms of Vn and Vout. Basically all of the equations are flipped from NMOS operation. If you recall, PMOS, it's basically the same relative equations, but instead of ground you have VDD instead of your threshold voltage. One thing to keep in mind is the threshold voltage for a PMOS, instead of being a positive value, is a negative value. So again, the equations get flipped in terms of greater than and less than are flipped relative to each other because you need to be less than VDD instead of greater than ground for an NMOS device. So for threshold or for cutoff region, our Vn has to be greater than VDD plus VTP. Keep in mind, V threshold for a PMOS device is a negative value, so as long as Vn is higher than VDD plus a negative threshold voltage, Vn is close to VDD, it can be a little bit less than VDD, but not less than VDD by whatever the absolute value of that threshold voltage of your P device is. And if that's true, you're close to VDD, then you're going to be in cutoff region. For linear operation, you need to be, Vn has to be less than VDD plus VTP. Again, keep in mind, VTP is a negative value, so Vn has to be less than some value which is VDD minus absolute value of a threshold voltage below VDD. As long as Vn is lower than VDD by enough, you start turning the transistor on and you're in the linear region. As long as Vout is greater than Vn minus VTP. And then for saturation region, you're in saturation if Vn is less than VDD plus VTP and Vout is less than Vn minus VTP. So those are the equations. Just keep in mind that you need to, in order to be in saturation region, your Vn has to be low enough to turn the transistor on, and Vout has to be lower than Vn by enough value to go into saturation. So as I mentioned a couple foils ago, rather than going into the gory details of the equations of current versus voltage, we're going to go through more graphical depiction of current versus voltage and see how the behavior of the devices go based on the graphical nature, to hopefully give you a little bit better understanding rather than just trying to memorize equations. So in here we're showing what a NMOS voltage versus current, which is the green waveforms in the upper right quadrant, versus the PMOS current versus voltage, which is the blue waveforms in the lower left quadrant. So in this case, I've mentioned before that usually PMOS transistors have a lower mobility than NMOS. So we're making the assumption here that we're making the PMOS device a little wider than the NMOS, and we're making it wide enough that we actually cause the beta N to equal the beta P. So the curves here are the same magnitude value for a given VGS value, because of the fact that we made the PMOS wider than the NMOS. So this graph here is showing if we took the previous foil and instead plotted the PMOS and NMOS both in the same quadrant, instead of plotting the PMOS device relative to the drain and going negative, we plot it relative to VDD and go to ground. The blue curve would be how much current would be going through a PMOS device depending on the gate voltage and the output or drain voltage. And the green curve is the amount of current going through an NMOS device depending on its gate voltage and its drain to source voltage. So here, if we assume that the VN values, VN 1, 2, 3, 4, and 5, are, and VN 0, in the case of the blue curves, are if VN is that many volts, and assuming our VDD is 5 volts, just as an example, this is the type of curves we would get. So for an NMOS device, there's no VN 0, because if you had the input equal to 0, you just get, you're in cutoff and you get 0 volts out, and so there's no graph for that. But if VN is 1, you have a fairly low gate to source voltage. You're going to be in saturation most of the time, but you have a flat line pretty close to 0 current. Depends on what your threshold, if your threshold voltage was 0.8 or 0.9 volts, VN1 is just barely turning it on, and so that's why the curve is so close to ground there. In the case of the PMOS device, you're most turned on when your VN is 0, and so that's why that's the highest curve. For your NMOS device, VN5 is your highest voltage for your gate, and that turns the NMOS on the most, and so that's why you can see the NMOS curve is the highest with VN5, PMOS curve is the highest with VN0. If we were somewhere in the middle and we had VN2 for one of the curves, so like VN2 for the NMOS device would basically be at the same time the PMOS device would be in effect at VN2, and both of them would want to turn on some amount if V out was somewhere in the middle. And so you can see if you had VN equal 2 and V out was in the process of switching between 0 and ground, you would get current through both devices at the same time. So if we do a load line analysis of an inverter, so we have our inverter drawn over to the right hand side, lower right corner. We have an NMOS and PMOS connected in series with each other. So one is considered to be the load of the other, or vice versa. So for a given V in, if we want to plot the current through the drain to source of the N and the current through the drain to source of the P, they have to be equal to each other. And we need to figure out what V out value we would get based on drain to source and of the P and N being equal to each other. So V out must be where the currents are equal. So how would we go about doing this? So let's do some load line analysis example here. So first let's assume that our Vn is 0. So at Vn 0, if we go back to the previous slide set, we have the curve for the blue curve, which is the PMOS Vn versus Vout curve. And that has, with Vn equals 0, it's going to be a high current when Vout is 0, and it's going to be 0 current when Vout is equal to VDD. Keep in mind, though, that our Vn 0 curve for the NMOS device, which is the green curve, is NMOS when the gate source or gate to source voltage is 0. NMOS device is cut off, has 0 current. It's just a flat line at 0. That's why you don't see the green curve there. But where those two curves intersect is basically at the the current value is equal to 0. And so that's why the red dot there is at where VDD, basically it's equal to VDD is what our Vout has to equal, and we have 0 current. So now let's look at if Vn was 20% or 2/10 of VDD. So Vn is 0.2 times VDD. So if our VDD is 5 volts, this would equal Vn1. So if we go back to the previous foil, look at the Vn1 curves for blue and green. The green Vn1 curve was just a little bit higher than 0 current, but mostly a flat line close to the 0 current line. The Vn1 line from the previous foil was fairly high current most of the way and then tails off toward 0 current near the end. So here you can see the intersection between those two curves is a little bit higher current than 0, but the voltage is still pretty close to VDD. So at Vn equals 20% of VDD, Vout is going to be pretty close, 90%, 95, 99% of VDD. It's pretty close to VDD. Now let's go to Vn equals 0.4 times VDD. This is the Vn2 curves of the previous slide. So here you can see the green curve is now a little bit higher. The blue curve is starting to get lower. The green curve meets the blue curve, still close to VDD, but it's not quite VDD anymore. Maybe 90% of VDD or so here. And you can see there's starting to be a little bit of current flow, measurable current flow. It's not close to 0 anymore. So that's interesting to note. Now when we get from 40% to 60% of VDD, our blue and green curves kind of flip each other. Now the green curve has more current than the blue curve, and where they intersect is now way down close to 0, close to ground. And so our output voltage in this case, when Vn is 0.6 times VDD, or Vn3, our output voltage is probably 10% of VDD or lower. It's pretty close. It's getting pretty close to ground. And when we get to 80% of VDD or Vn4, now it's the flip. It's close to flipped of the 20% of VDD that we looked at, where Vn4 has the PMOS device is pretty much turned off, but it's still on a little bit, and the NMOS device is pretty heavily turned on. So our voltage is really close to ground, not quite zero, but it's pretty close to zero. And finally, when VN gets all the way up to VDD, our PMOS device, its curve is basically fully turned off and it's at zero. So our output voltage is going to be where our NMOS device curve hits zero, which is at Vout equals zero. So when we look at the full set of curves here, we'll see for changing our Vin between 0 volts and 5 volts, we get an output voltage that, at least for the points that we plotted here, the output voltage is going to be pretty close to either 0 or pretty close to VCC for most of the choices that we have, or for all of the choices we have here. And we would have to find something in between VN2 and VN3 in order for our output voltage to be somewhere in the middle of the range instead of being close to VCC or VDD or via or ground. So now instead of just plotting this at discrete VN 1, 2, 3, 4, 5, if we actually swept our input voltage at every voltage between 0 and 5 volts, we would get something that looks like the graph on the right hand side there, where you can see at VN 0, 1, and 2, we've got a curve that stays pretty close to a Vout of VDD. And then when we get to 3, 4, and 5, we have an output voltage that gets pretty close to ground and stays pretty close to ground most of the time. And it's only when we get to that voltage that's exactly halfway between VDD and ground that we have a really fast switch of Vout between VDD and ground. So as when VN hits exactly halfway between VDD and ground, we'll get something around Vout halfway between VDD and ground as well. And that will happen if the PMOS and NMOS are exactly balanced with each other in terms of drive strength. Then we're going to get Vout equals half of VCC when Vn equals half VCC, as long as if they're completely balanced. If one of them's a little bit stronger than the other, we won't have that switch happen exactly in the middle. But no matter what happens when we have something like an inverter, we will get a curve that looks similar to the curve on the right hand side there. It's just the exact point at which the switch happens quickly between VCC and ground will change a little bit depending on the strength of the NMOS versus the strength of the PMOS. But the key thing to remember is we will get a curve we'll pretty much always get a curve that looks similar to that curve on the right. And so let's discuss the kind of nature of that curve and what it means in terms of our behavior. So in effect, we have a couple different operating regions here for our NMOS and PMOS. And so let's revisit those and look at what's going on in each of these different regions that we're operating in. So first, in region A, where our input voltage basically is less than the threshold voltage of the NMOS transistor, the NMOS is cut off, and the PMOS is in the linear region. And that's because our output voltage is basically high enough or close enough to VDD in that region where the PMOS is now no longer in saturation. So the PMOS is fully turned on, but the drain to source voltage for the PMOS is close enough to VDD that the PMOS is in linear region. So in region B, the NMOS transistor is in saturation because the NMOS is turned on. The input voltage is greater than the threshold voltage, and the gate voltage is greater than threshold voltage, and the drain voltage is really pretty high. It's all the way near VDD, so the drain voltage is much greater than VGS minus VT. And the PMOS device, though, is still in linear region because the PMOS device has, since Vin is so much lower than VDD, the PMOS device has its VGS is turned on well enough, but the drain to source, since the output voltage is still so close to VDD, it's only in linear region. When you get to the middle of the range, where you're in the region where you're switching quickly between VDD and ground, both your NMOS and PMOS devices are in the saturation regions. So you actually get a lot of current flow through both of them. And then everything flips when you get into region D. It's kind of flipped from region B, where your NMOS device is now in linear region, your PMOS device is in saturation, and then finally in the last region there, your PMOS device is basically turned off in cutoff region, and your NMOS device is in the linear region, and there's not much current flowing just because you're so close to your output voltage is so close to VSS that it doesn't have much current going through it anymore. So in the previous foil, I had mentioned that if your NMOS and PMOS transistors are really well balanced, such that your beta P and beta N are equal to each other, then you're going to look like in the curves below, the one that is labeled with a 1, beta P to beta N of 1, your transistor or your inverter is going to switch, output voltage is going to switch between 0 and 1 as input voltage switches between 0 and 1. When they both get to the 50% point is where that steep part of the curve is. So 50% of VDD for the input is going to cause 50% of VDD for the output, and it's going to switch really quickly. Small change in Vin is going to cause a very large change in Vout right at that 50% point. But if your beta P to beta N ratio isn't equal to 1, basically we call this a skewed gate. So you can skew the gate to be higher skewed toward P or lower skewed toward P. So if your BP to Bn ratio, your P is much larger than N, that's called a high skew gate. So your PMOS device is a lot larger, a lot stronger than your NMOS. And if your PMOS device is a lot lower than your NMOS, that's called a low skew gate. So what winds up happening is, as your PMOS device gets stronger, it takes a higher input voltage to cause that switching point of your output going from a 1 to a 0. And the reason for that is, as the PMOS device gets larger, in order to equalize the current between the N and P, to cause equalizing the current would cause your Vout to hit the middle, you need a higher voltage on your NMOS gate to pull more current through the NMOS, and the higher voltage on the PMOS causes it to have less voltage or less current. So you need a higher voltage to get the NMOS larger current, PMOS smaller current, such that they equal each other and cause that high switching point. And conversely, if your PMOS device gets smaller than your NMOS device, you need a lower voltage to hit that switch point. So in other words, as you change your P to NMOS sizing, you can change the effective place where your logic gate switches between 1 and 0. So a high skew gate will switch at a higher value of Vn will be needed to switch from 1 to 0, and a low skewed gate requires a lower value of Vn to switch from a 1 to a 0. And this will get into other side effects later on that affect things like the timing, how long it takes to switch logic values, how fast you can switch logic values, and the timing of your circuits, and what we'll get into next, which is noise margins, which is an important concept as well.